We've been talking about galvanic cells and electrochemistry, and last time we talked about a couple of sort of relationships. We talked about the relationship between delta G and the E of the cell is equal to delta G is equal to minus NF E of the cell here. And again, as we talked about, these two things agree with each other. If we end up with a positive cell voltage because of the negative here, that will turn our delta G into a negative, which would be a spontaneous process. And again, obviously, we would have positive voltage. And is the number of moles of electrons. F is Faraday's constant, 96,500 joules per volt per mole. We also saw the relationship between E of the cell and K. RT, NF, natural log of K. Again, these are all kind of the same ones as above. Our moles of electrons, our Faraday's constant, our temperature in Kelvin, obviously, in most cases. Again, that is the R that is involving energy. So that's the 8.314 version of it. And obviously, K is our equilibrium constant. So all three of these sort of values, again, as we saw in some of those examples, do agree with each other. Again, if you have a delta G that is negative, that should probably give you an E of the cell that is positive. And because it's a spontaneous reaction, we have forward sort of movement there towards the product side. That should give you a kind of larger value of K. Opposite is true if we had a positive value for delta G, that's probably a result of a negative value for E of the cell, as again, the negative here and here will turn this guy into a positive. And because of that, that means pretty much it's a non-spontaneous process. Reactants are favored. And if reactants are favored, obviously, when we get to our equilibrium constant, we are looking at a small value. So once again, all those things, as we see in problems, thank you, should agree with each other. We also saw sort of our galvanic cell version of non-standard condition, which is the Nernst equation, which E of the cell is equal to E naught minus RT NF natural log of Q. And once again, this would be used in a sort of non-standard conditions. Remember that pretty much non-standard conditions has to do with molarity. They have to be kind of 1 molar to be standard conditions, and anything to doing with pressure should be 1 atmosphere or 1 bar, which would also be sort of standard. So if you have any situation where you have kind of concentrations given to you or pressures given to you, as again, you could do a galvanic cell, obviously with a gas sort of electrode, if you will. If they are not in those sort of conditions, then you would need to do this. This is our normal E of our cathode minus E of our anode. And again, obviously, as we talked about a lot, obviously subtracting, we're not going to change the sign that we find in the table. Obviously, if you do change the sign, you should add those numbers along the way. The rest of these guys are the exact same as above, and obviously our Q is our normal Q, which is our products, right, divided by our reactants. Right? So what this allows you to do, and I think what would happen in that sort of last example that we did, you under sort of standard conditions have a galvanic cell that maybe is not going to sort of head to the products, and by playing with maybe the concentrations or even the pressures, you can maybe get a little bit of voltage to come out of that particular cell. Any questions on that there? And as we also talked about, that's basically how you could get to that formula, because at equilibrium, Q will equal K and E will equal 0. And if you rearrange this equation, you basically get this equation here. All right, then let us continue on. I think we got this one to go. So for the following, let's just calculate E and K as well here. Okay, let's take a look. So obviously here we're looking for E and K. So we got a few formulas. So E of the cell is going to be our cathode minus our anode. And obviously, the one that we saw there, E of the cell is equal to RT/NF, natural log of K in this case. So we do need to start with this. In this particular case, we actually do need to figure out what is our anode and our cathode. So if we take a look over here, that's a -2, gets you a -12, gives you, we got there, -12, it is equal -2, so we got there, maybe like a 2.5, maybe something like that. And for the chromium there, +2, this chromium +3, and on this side, -2 is -6, so maybe like a +2 happening in this particular case. So here we can see chromium going from +2 to +3, so it is definitely going through oxidation, heading in that direction, becoming more positive. So the chromium here would be our anode, and this guy would be our cathode, as it's gone from 2.5 to 2, which is slightly moving in that direction, negative in that particular case. Again, a reminder, as we talked about also last time, if you are given the equation like we were in this one, you do want to make sure you take a look at it and make sure you know who's being oxidized, who's being reduced. Remember, we want to only use the SRP values if you're not given any type of overall reaction or information on how it's happening. So in this case, it actually does sort of follow what you would have chose anyway. So you would have lucked out in this case. So the cathode here is obviously going to be our S4O2. We can also see that's on the left-hand side and that's on the right-hand side, which definitely would also have told us that we would have had to reverse this guy to get it on the correct side. Also, by the way, times it by 2 to balance out the electrons that are over there. And our E there, if he flipped it around, would technically be that right there. So in this particular case, we'll calculate our E of our cell, and that's going to get us here. And I guess I could throw some numbers up here, 2 and a 2 and a 2 actually there. And that's going to be our cathode, which is 0.17 volts. I'm going to subtract, so I'm actually going to use the SRP value without changing the sign. Obviously, if you change the sign like I did below it, you should add these numbers, as we talked about a number of times. And obviously, that is going to turn it into a positive, and we will end up with a cell voltage of 0.67 volts. That is a positive value for E, which means that we should probably have a negative value for G, which means this reaction should be spontaneous and product favored. And that probably should give us a good value there for K, or a larger value for K. All right, so some of the other stuff there, our temperature, obviously adding our 273, going to get us a 298 Kelvin. R's our constant, 8.314 joules per volt per mole. The N as well, also maybe want to take a look and balance it. And in this case, remember, is only 2, not 4. And Faraday's constant obviously is our constant there. So 96,500 we'll use joules per volt per mole there. All right, so we can then go into our equation here, and we will end up with 0.67 volts equals our 8.314. It's the wrong one there. Okay, I'm gonna run out of room, so I'm gonna back it up, I think. Going to just not do that. Maybe I'll go below here and do it. All right, so going into our equation with a little bit more room. We'll go 0.67 volts equals our R, 8.314 joules per Kelvin per mole. Our temperature, 298, divided by our 2 moles and our 96,500 joules per volt per mole. And that's going to be a natural log of K. So I'm going to kind of clean up this side, and we'll see what we got going on. 8.314 times 298 divided by 2 divided by 96,500. Going to get us here 0.012837 equals 0.67 volts. Natural log of K. Obviously, we're going to divide that to the other side. So 0.67 divided by that. Going to get us here 52.19 equals the natural log of K. Going to E both sides there. That's going to get rid of that. And I'm going to use the whole number, not the rounded number. And I'm going to yield something like 4 we'll call it 6 times 10 to the 22 as our equilibrium constant. Once again, with rounding, you might get a slightly different front number if you round it a little bit when you do the E. But once again, as I mentioned before, all those things sort of agree. Positive voltage, again, means spontaneous delta G. Negative, products favored means more products than reactants. So again, a large value of K. So once again, all three of those values should show to agree with each other. Any questions? Any of that there? Okay. The next thing we're going to talk about are batteries a little bit. And we're going to go over a few different types of batteries, and you're not necessarily responsible for individual battery reactions or anything like that. You just need to know how batteries are similar, maybe how they're a little bit different than a traditional galvanic cell. Heck, that might even be the actual question right there, by the way, just so you know. Batteries are galvanic cells or series of galvanic cells that are can be used as a direct electrical current at a constant voltage. Obviously, benefits of a battery versus a sloshy beakers. They are self-contained. No need for a salt bridge. Hard to put beakers and salt bridges into equipment and stuff. So we'll take a look at this battery here. I'm gonna go with Duracell, maybe. Let's see. Um, this is sometimes referred to as a dry cell, so it's a cell without a fluid compartment. It has an anode, which is a zinc can, uh, our container that's in contact with MnO2 and an electrolyte, which kind of serves almost like a salt bridge to kind of keep everything kind of flowing. We have a carbon rod that's in the middle there. In the electrolyte center, and obviously we have the negative side of the battery right in the positive side, just kind of like in a galvanic cell. Electrons, the zinc anode, so electrons going that way, right out through the wires that's in the battery compartment. Those electrons are used obviously to power whatever you got going on there. This type of battery, regardless of sort of the size, will give off a 1.5 volts of C's versus triple A's versus double A's. They are given out about 1.5 in terms of its voltage. Obviously, bigger batteries can last a little bit longer along the way. Here we see our anode again going from 0 to +2, so getting oxidized the zinc part of it. And again, our reduction sort of happening here on the bottom. We have our Mn, which is +4 over here, +3 getting reduced in this case. And this is our overall reaction. Again, electrons basically traveling that way. Mercury batteries used a lot in medicine, electronic industry. They're more expensive than obviously your typical alkaline Duracell. They also have a similar sort of setup. They got a zinc anode that's in contact with mercury. It's in a strongly alkaline electrolyte. Alkaline means basic, so something like a strong base like potassium hydroxide. And once again, sort of those battery acid, if you will, or that type of stuff that we kind of refer to it of the center part. Again, sort of acting as like a salt bridge, trying keeping everything flowing in the right sort of direction. There's no change in the electrolyte composition during operation, so that does give it a very long life, and that's one of the things that's good for batteries in a sense is if you look at the overall reaction, you have a lot of solids and no real changes happening in terms of the states, and that allows for sort of longer life and higher capacity. You have a little less of a voltage in this type of battery, 1.35 volts. And again, we do see kind of our zinc going from 0 to +2 getting oxidized. Here we have a little bit of mercury going from +2 to 0 getting reduced in this case in this type of battery. Lead storage batteries, which are commonly used in Automobiles, they are six sort of cells together. Each of them gives about 2 volts, which is about 12 volts for your car battery. And that's usually enough to start everything and get your car turned over, unless, of course, you're late and it will not turn over and gets stuck. But most of the time, it will start in those cases. And it is rechargeable, right? If you ever need to jump your battery, right? They tell you let it run for a while, right? It's kind of recharge it up, and it's able to do that. Healthy battery can be checked usually by looking at the density of the electrolytes, or that sulfuric acid sort of in the middle there. And here's sort of a cross section of a battery, right? That you typically find in a traditional car, and where they put them these days, sometimes in the trunk on the back seat, but usually you can find at least the connectors, if you will. There's our negative and our positive, right? Our anode and our cathode. And obviously this is where you hook up your jumper cables if you need. And here's our strong electrolyte in this guy. And again, kind of hooking these up in a series, you get the benefit of adding all those voltages together. So our lead here going from 0 to +2, getting oxidized in this case. And in this particular case here, we got a +4 and a +2 happening in that case, also getting reduced as well. So here we do see a lot of solids sort of made and liquids. And again, that's really good for sort of rechargeability along the way. And again, giving us sort of a longer life as well. Lithium batteries or solid state lithium batteries work a little bit different in a sense. They do have some type of conducting carbon graphite type of material that has holes in it for the lithium to sort of travel. So when it loses electrons, it will allow the lithium ions basically to travel through that solid electrolyte. A cathode is usually some type of transition metal, like cobalt for oxide, that can also hold some of those lithium ions when they get to the other side. Can be recharged hundreds of times without a deterioration. Also, it's a light metal as well, so a lot of tools and stuff, right? Lithium batteries are used for those purposes as well. Now, a fuel cell, which is not necessarily a true battery in a sense, but sort of acts like a battery. A fuel cell is really an electrochemical one that needs a continuous supply, and this is a hydrogen fuel cell in a complete supply of hydrogen and oxygen happening in this case to be supplied here again with a pretty strong basic sort of solution here as an electrolyte to keep everything flowing. Here are hydrogens going from 0 to +1 being oxidized, oxygen going from 0 to -2 being reduced in this case. This was originally what they wanted to sort of build cars into, was like a hydrogen fuel cell. As obviously you can see here in the overall reaction, that's all you get there is water that's made there. That didn't work so well, I guess. And so we're now moved on to obviously hybrids and full battery sort of cars as well. All right, so let's talk a little about corrosion. And corrosion is really the returning of metals to their natural state. Fifth of steel production is to sort of replace rusted metals. All metals that have a SRP or standard reduction potential less positive than oxygen are susceptible to go through corrosion. And that is because if you have a metal that is less positive than oxygen, so he is more positive, right? Less positive. When you think about it in sort of a galvanic cell situation, the oxygen here is going to be your cathode and your metal is going to be your anode. And that means that your metal is going to go through oxidation, which is basically corrosion that's going to happen. So that's why certain metals with SRP values less positive than oxygen will just start to corrode sort of spontaneously, because you'll get a really spontaneous galvanic cell sort of reaction that's occurring. Now, not all sort of um, corrosion is necessarily bad. Sometimes when metals do go through corrosion, they do actually protect further corrosion because they do create sort of a little layer of corrosion that protects the fresh metal underneath it from further corrosion. So aluminum is an example of that. It forms this aluminum oxide, which inhibits it. So the idea there is, even though some of it does go through corrosion, it makes this sort of layer of protection for the kind of other metal underneath to not go through that sort of continuous corrosion. That also happens with iron, but the problem with iron, for example, is it does fall off. So even though it kind of creates a little corrosion layer, basically rust will fall off, and then that exposes fresh metal to continue that process until you got like no metal left, right? It just kind of corrodes right through it. Obviously, the corrosion of copper is sometimes very expensive, right? It creates that nice patina people like, that sort of color. Silver or tarnish, it makes silver sulfide. Gold, which has an SRP value of 1.5, which is larger than oxygen. So when gold hooks up with oxygen, gold's actually more positive than oxygen. It's less positive. So again, in terms of a galvanic cell, that would mean gold would actually end up being the cathode where reduction would occur, and the oxidation would actually occur over here at the oxygen, which would be our anode. So again, would not go through uh, a lot of corrosion with air because again, it's not sort of favored in that sense, because again, gold's going to be your cathode. Steel, as we talked about, as I just mentioned, does go through oxidation, and iron actually gets oxidized twice there. It actually goes to iron 2, and then the iron 2 gets further oxidized down the road there to iron 3 and makes iron 3 oxide, which is basically rust. Again, you basically just need a few sort of things to come together for rust to form. You need a little bit of moisture, you need some iron and some oxygen, which is plenty. And because steel has these non-uniform points on it, it's a good place for moisture to sit on top of the iron. Obviously, there's oxygen in the air, so those are all conditions where it's pretty ripe for rust to start to form on that. Like I said, the problem with that is, again, it falls off, and now you can just kind of continue doing that, costing a lot of money along the way, I suppose. Now, there are a couple ways to prevent corrosion. And in terms of corrosion, you just need to kind of know what it is and maybe a couple of ways to prevent it. So, a couple of ways that you can prevent corrosion. I could use something like painting or do some type of metal plating, right? They sell rust-stolen paint. I imagine that they called that for a reason, right? So it provides a layer of protection over the metal. Chromium tin can be used to plate steel because they do form a more durable sort of layer that will protect it. Galvanizing also as well, since zinc is a more active metal than iron. So when you galvanize something, you pop zinc in there between zinc and the iron actually is more positive, which means it's going to kind of move into the cathode role. This is less positive, which means it's going to move into the anode role. And that is where your sort of oxidation and corrosion is going to occur for the zinc, sort of a sacrificial sort of coating that will protect sort of the metal that's underneath it. You could also do some type of alloying. So stainless steel contains chromium and nickel, which again forms a nice oxide coating and also changes it to a more reduction potential similar to noble gases. So it has that ability with those extra metals in there to kind of change the SRP value and again prevent it from going through serious corrosion. Cathodic protection is another sort of idea there. For example, if you bury a tank or something in the ground, there's obviously a lot of moisture and stuff in there. So you could do something like magnesium connected to the tank by a wire. Magnesium is a better reducing agent than iron. Remember, the reducing agent is the one that gets oxidized, right? So that means magnesium here is going to also act as a sort of sacrificial place for the oxidation to occur, hopefully away from your big tank that you just spent a lot of money to bury into the ground. You don't have to dig it up every 2 weeks, right? And stuff like that. And it should last hopefully for a good period of time. Titanium is used again in ships because obviously with a lot of salt and stuff like that. So here again, an underground sort of storage tank. We got this guy where all the oxidation is going to occur over here on this end, hopefully leaving your tank not to go through oxidation and be in good shape. Any questions on corrosion and batteries? So batteries, again, just kind of need a generally similar and difference between traditional galvanic cell and corrosion, what it is. A couple ways to kind of protect against it. Any questions on that there? All right, the last thing we're going to talk about in this chapter is electrolysis. And electrolysis is the process where we make a sort of non-spontaneous process occur by providing some type of external electrical energy that is used. So, for example, if we had something like sodium chloride, we cannot return it, if you will, back to sort of its elements by a natural process. So if you have sodium chloride, it's just going to not spontaneously just come up to sodium gas or sodium metal and chlorine gas. But if you apply an external sort of source like a battery, you could kind of force this non-spontaneous process to occur. It is important that when we talk about electrolysis, it is opposite, if you will, of a lot of times what we normally associate that's going on. And what I mean by that, what's sort of the anode and the cathode in an electrolysis cell is different than what you might think. Because let's just take sodium chloride as an example. When we think about making sodium chloride, this is the reaction that's happening basically in this direction when we make it. And when we make it, obviously, we can do a little balancing, maybe like in the chemistry class. There we go. But in terms of what's happening as we sort of make sodium chloride, the sodium here is going from 0 to +1. The chlorine is going from 0 to -1. So when you make sodium chloride, the sodium is getting oxidized, which means it would be your anode. The chlorine here is getting reduced, which means it's your cathode. Now, in an electrolysis cell, you're already starting with the sodium chloride, and you're breaking that thing into sodium and chlorine. Now, going in this direction, when you break it apart, the sodium is going from +1 to 0, and the chlorine is going from -1 to 0. So it is actually opposite here. The sodium is actually getting reduced, and it is going to be your cathode. The chlorine here is going again from -1 to 0, which is actually getting more positive, and it's going through oxidation, and it's going to be your anode. So sometimes people think about electrolysis cells, they think about like the ionic compound kind of making it, and they always get kind of the cathode and anode backwards in that case. So you want to be really careful on that. And that's what we do see here in the sort of breaking it apart. We're going from -1 to 0, again becoming oxidized. Sodium going from +1 to 0, again getting reduced in this case. So in this case, the electrons are actually flowing from our chloride back to our sodium in this particular case, which is opposite of when you make that ionic compound is flowed in that direction. We could also do electrolysis of water, which is a common run, right? So if we run an electrical current over water, you could do this in the lab pretty easy with a 9-volt battery and all that good stuff. You could break apart basically water, and you can break apart obviously into something like this. And in this situation, same idea. It is opposite of when you make water. So once again here, the hydrogen is going from +1 to 0. The oxygen is going from -2 to 0. So in terms of our oxidation, we can see that the excuse me, the oxygen is going from -2 to 0, so it is getting more positive. So this is going through the oxidation, and that would be our anode in this case. Hydrogen here is going from +1 to 0, which is becoming more negative, and is going through reduction, which would be our cathode in this case. Now, in order to do this, you usually need to build up a little bit more acidic sort of water than just regular water. So the extra hydrogens in that water help kind of keep everything moving and work more efficiently to do so. So we'll usually have some type of acid involved in the electrolysis of water. And if we look over here, that is what's happening in this picture. We're doing electrolysis of water. And over here in the empty spot of our test tubes, that's where our hydrogen gas is. And that is where our oxygen gas is in the blue. And we actually see a lot more hydrogen than oxygen. And that's because it is H2O, right? So twice the hydrogen than the oxygen. We actually collect that when we do that gas. Now, when you're doing the electrolysis of water, you can see the overall reaction here. And once again, -2 to 0 and +1 to 0 here. Now, I will say that when you read an electrolysis problem that involves water or the electrolysis of water, they sometimes, and very common, don't even mention like the electrolysis of water. They will more so just mention that you did an electrolysis cell with some type of acid, so like a sulfuric acid or something like that, or dilute sulfuric acid. So that's the key words of like, hey, it's the water hydrolysis or electrolysis that's happening here. So very commonly, sometimes they will mention like water going through electrolysis, and they'll just kind of mention something about an acid. So probably a safe bet if you come across a question like that that kind of mentions a dilute acid solution or dilute sulfuric acid solution, like it shows there, they are referring to really the electrolysis of water. And if you need some half reactions, then obviously these would be the one for water that you would want to use in that particular case. Questions on that there. Now, in an electrolysis cell, we can actually calculate a few different things. We could actually calculate how much, for example, metal we might get out, how many grams of something. We could also calculate some other things. And in these type of problems, it's usually run in one of two directions. So we'll just talk about this direction of the calculation. You're typically given the current in amps, and an amperage is equal to a coulomb over a second. So that's a good kind of conversion. So usually you'll give the amperage of the cell that's running, and that's basically is a coulomb per second. Coulomb, a unit of electrical charge, obviously a second. You also will be given the time, usually, of kind of how long you let the cell run for. And the time obviously can be in any unit, but usually you kind of want to get the unit of time into seconds as well. And that is because you have the current as well. So usually kind of the beginning of this calculation is you take the seconds of how long the cell ran for and you times it by the current it ran for. And that will give you basically the coulomb of charge that's happening in that particular cell. Once you do that, you can actually use Faraday's constant as a conversion factor to go from coulomb of charge, which is 96,500 coulombs per mole of electron. And this will eventually get you to moles of electrons. So that's a pretty standard sort of opening to a sort of electrolysis sort of calculation. The ultimate goal here is to get to the moles of electron. Now, once you get it to the moles of the electrons, this is where sort of your half reactions, your anode and your cathode half reactions come into play. So you would have obviously a oxidation half reaction or an anode half reaction, right? And that obviously would have, go with a metal and a metal plus and an electron. You'll have something coming off like so. And you'll also have an anode or a reduction one, or cathode. And obviously that would gain some electrons, right? Maybe. And we'll do that. So at this point, once you figure out the moles of electrons are sort of being generated in this electrolysis cell, you can use each of these half reactions to do really just like a stoichiometry, moles of electrons to say moles of the metal. So in this particular case, this would be like 1 mole of electrons gives me 1 mole of my metal, whatever that metal may be. And you can use that as a conversion factor to go from moles of electrons to moles of the metal. At that point, you could use something like molar mass to figure out how many grams you would produce, right? Because you have the moles of the metal. So very commonly, you could then kind of go from moles of the metal to grams in the molar mass from the periodic table to do so. You also could do that for the non-metal as well. That might be there, and you can figure out grams. Now, sometimes though, as we saw in that last couple of sort of pictures of those electrolysis cells, what we're actually producing are gases. So very commonly as well, since we are producing gases, sometimes people want to know the volume of gas that you're going to sort of collect. So that's going to bring us a throwback favorite equation, right? PV equals nRT is sometimes used in these type of problems, especially if we're looking for the volume of a gas is going to be generated in this case. Obviously, you would have the temperature. R is your gas constant. Remember that when you're using the ideal gas law, it is the other R value, right? The 0.0821 or 206 version of it. Obviously, you could figure out your moles and you'll have the pressure. So sometimes you are asked to sort of solve for the volume here, and you might have to use the ideal gas law to do so. A reminder that when you use the ideal gas law as well, you got to be really careful with units, right? So once again, pressure has to be atmospheres, volume should be liters, temperature should be Kelvin, and obviously moles should be moles, right? So got to make sure everybody's in those units, obviously, if you use that. So those are kind of two endings to this type of calculation where either you'll figure out how many grams you would produce or maybe how much volume of a gas you would collect along the way. Any questions on that? Variations of this type of problem is maybe you're told how much you actually made or produced in grams of something, or how much volume you produce, and you go backwards in this calculation to figure out maybe how long you ran the cell for, or what was the amperage, sort of the backwards version of this calculation, starting backwards and going to the front. All right, so let's take a look at one. Actually, we'll come back to this one here. Let's see this one here. So we want to know how much calcium will be produced in an electrolysis cell when we start with molten calcium chloride and we run a current of 0.452 amperage and it's passed through the cell for 1.5 hours. Okay, so let's take a look at, so we're doing obviously electrolysis cells. So as we've been talking about, again, sometimes people, when they're maybe trying to figure out anode and cathode, sometimes we'll get things backwards. So in this case, we're actually breaking this guy apart, kind of back into its elements, if you will. So we are going to end up with this. And in this particular case, the calcium on this side is going from +2 to the other side where it's going to be 0. The chloride going from -1 to 0 in this case. So once again here, it is the calcium that's actually getting reduced and is the cathode in this case. It is the chloride that's going from -1 to 0, which is becoming more positive, that is going through oxidation and would be our anode in this case. So if we write sort of our anode and cathode sort of reactions, if I didn't kind of write it right over where that was going, get rid of that there so you can see it. There we go. We have our chloride again going from -1 to 0, and our calcium going from +2 to 0 in this case. All right, so now we got that sort of straightened out. We are given the current here, which is 0.452 amperage, and that is the same as 0.452 coulombs per second. Here we are running it for 1.5 hours. So once again, we really do want the time here into seconds so everything cancels out correctly. So in an hour, there's something like 3,600 seconds, right? So I'll go 1.5, let's you, times 3,600. Going to give us 5,400 seconds. So now we can use both of these together to figure out our coulomb of charge. So we're going to go 5,400 seconds times our 0.452 coulombs per second. That is going to cancel. And that will get us here, looks like 2440.8 coulombs. At this point, we will use basically Faraday's constant to convert this into moles of electrons. So there's 96,500 coulombs per 1 mole of electron. And again, the coulombs here are going to cancel. And now we will end up with, looks like maybe 0.0253 moles of electrons. Any questions on the first part here? Now that we have it really in these moles of electrons, we're good to come into really both of these half reactions if we wanted to and figure out what's going on with our calcium and our chlorine. But in this case, we're going to do the calcium, which was what the question was asking about. So if we go to our cathode reaction here, we can see sort of a mole-to-mole relationship between our electrons and our calcium. And we see for every 2 moles of electrons, we're going to get 1 mole of calcium produced. That's really just going to be our conversion factor here to go from moles of electrons here to moles of the calcium. So again, from really the balanced half reaction, 2 moles of electrons, 1 mole of calcium. And that will get us here divided by 2. Looks like 0.0126 moles of calcium. Here we're looking for how many grams, so we'll use the molar mass from the periodic table there for calcium. And at this point, looks like it is 4008 grams per mole for calcium. And so we'll times that by 4008. It looks like we will pick up something in the ballpark of 0.51 grams of calcium would be produced in this particular cell. Question. Now, it wasn't asked in this problem, but again, if you were also interested in the chlorine gas that you would collect, you could also still pick up from here and basically do the same sort of calculation using the chlorine's half reaction, which we would also see is actually a 2-to-1 relationship. 2 moles of electrons, 1 mole of chlorine gas. Going to get us basically 0.0126 moles of chlorine gas. Now, again, maybe you were also given a temperature, some other sort of gas information. You could use the ideal gas law if you had that information to solve for volume. Or you could also go grams as well by doing the molar mass of Cl2, and you can figure out how many grams of the chlorine gas you would produce. So since I don't have the other sort of gas information to go into the ideal gas law, 3545 times 2 gives us 90 grams per mole. And we would produce, in terms of grams of that gas, something like 0.89 grams of chlorine gas in this particular case. Any questions on that there? So pretty standard sort of calculation. Like I said, you could kind of work your way backwards if you were told, like I said, how much you were produced and figure out, how long you ran the cell, what was the amperage of the cell, that type of sort of calculation. Any questions on that one there? All right, let's try one more here, which is our friend here. A current of 1.26 amperage is passed through an electrolysis cell containing sulfuric acid for 7.44 hours. Write the half reactions and calculate the volume produced at STP. Also a throwback, that is standard temperature and pressure. Hopefully you remember the temperature is 273 Kelvin. Pressure is 1 atmosphere at STP. Now, as I was mentioning earlier, doesn't mention anything about water in this one, right? But it does say something about sulfuric acid or some type of acid. This is basically the electrolysis of water. So again, sometimes with the water, it doesn't just straight up say we're doing water here. I know I'll mention something about acid when you're doing it. So the half reactions are those ones that we saw earlier. So I'll let you kind of pick it up from there if you like. So again, we're running at 1.26 amperage for 7.44 hours at STP. We're looking for the volume hydrogen gas and oxygen gas you would produce. Again, in this case, we are given the amperage, we're given the how long the cells run for. So we can kind of do our normal sort of beginning here. We have 1.26 amperage, which is 1.26 coulombs per second. We also got 7.44 hours, which is how long we're running the cell for. So we'll get that into seconds. So we got everybody kind of in the right units here. So we'll do an hour is 3,600 seconds. So you can give us 7.44 times 3,600. You can give us like 26,784 seconds. So again, we could use both of that information there to get to our Coulomb here. So we'll do our 1.26 coulombs per second. That's going to cancel. And that's going to get us there 1.26. Looks like 33747.8 coulombs. Using Faraday's constant there, going to turn that into moles of electrons, so 96,500 coulombs per mole of electron. Coulombs will cancel, and we'll divide that by 96,500. Yeah, something like 0.3497, we'll call it, moles of electrons. Questions so far? All right, we're interested in both gases here, hydrogen and oxygen. So we're going to go to sort of both half reactions here and get ourselves some moles. So we'll go with oxygen first, which is on top. So in terms of oxygen, we can see from the equation for every 1 mole of oxygen, we get 4 moles of electrons. So 1 mole of oxygen will get us 4 moles of electrons. So taking our 0.3497 moles of electrons and using that sort of relationship from the balanced half reaction, we got 4 moles of electrons, 1 mole of oxygen. Moles of electrons will cancel. That's going to get us here, divide that by 4, 0.08743 moles of oxygen. We then can basically do the same thing for our hydrogen. And in this case, we do have a 4 on the outside, which does get distributed. So if you distributed that in, that would get you basically 4 moles of electrons, as the 4 would end up here. And 4 divided by 2 would give you 2 moles of H2. Or if you also want to reduce it down even further, you could do 1 mole of H2 would then give you 2 moles of electrons. So you can use either relationship that you want, but since that 4 is on the outside, we do need to distribute it in, and we'll just use the non-reduced version here. 4 moles of electrons give us 2 moles of hydrogen. So we'll use our same moles of electrons we calculated above. We'll use that relationship we just looked at there, and we'll have our 4 moles of electrons, 2 moles of hydrogen gas. Moles of electrons will cancel. And that's going to get us here, looks like 0.1749 moles of hydrogen. So at this point, we are looking for the volume of a gas. We are also given STP, which once again gives us a temperature of 273 Kelvin, a pressure of 1 atmosphere. And now we have moles. So once again, PV equals nRT. We have the temperature, we have the pressure, we have the R, and we also have the moles that we calculated. So we can solve for volume in this case. And we'll do it here for oxygen. So the volume of oxygen would equal nRT over P. And putting in our moles of oxygen, which was 0.08743 moles. Our R value 0.08206. Our temperature of 298 Kelvin there. And not 298, I'm sorry, 273. That would be STP, 273. 273, there we go. And divided by 1 atmosphere. Obviously here moles cancel, Kelvin cancels, atmospheres cancel, leaves us liters as our units. And we will end up with 0.08743 times 0.08206 times 273. Gonna get us, we'll call it a 1.959. liters of oxygen gas would be produced in this case. We could do basically the exact same calculation here for our hydrogen if you choose. And we'll do it here for our hydrogen. Volume of hydrogen would equal nRT over P. Really, the only change here is going to be we're going to use the moles of hydrogen, which is 0.1749. Everybody else here is going to be the same. And once again, we're going to be left with liters. So 0.1749 times 0.8206 times 273 going to get me 3.918 liters of hydrogen gas in this case. We do see what we saw in the picture. I got about twice as much, right? Hydrogen gas collected here than oxygen gas from our H2O. You might also have remembered from Chem 50 that at STP, 1 mole of any gas will equal 22.414 liters, which means you don't have to necessarily use the ideal gas law. You could have just took the moles of each gas because we were at STP and basically just multiplied it by 22.414 liters. And that would get you up there as well. So because it was at STP in this case, you could use that conversion. A reminder, though, that if you're not at STP, you should not use that conversion, right? You have to use the ideal gas law. But if you happen to be at STP, you could kind of shortcut the ideal gas law as well. Any questions on electrolysis? So apply an electrical current to make a non-spontaneous process occur. And remember, a lot of people do kind of screw up the cathode and the anode because it is kind of going backwards from where we'd kind of normally think of it, especially with ionic compound formation. Any questions on that there? That should wrap up.